Well, it's actually about real-time decision making, right? So, what I'm going to do, I think, is go a little bit faster over some of the material and sort of get to the end, and not to mention we're a bit over on time, so I'll try to save us some. And what I want to do is talk about real-time decision making, and especially what optimization what the implications of fast optimization are for real-time decision making, right? So, and the canonical application I'm thinking of is control, although it's a lot of other things as well. So, okay. And I think I'll go fast because I think people have seen some of these things, but I'll go fast. So I'll start with convex optimization. Just a quick, I'm going to go very fast over a whirlwind overview of sort of what it is and all that sort of stuff to sort of get to the real part, which is the real-time stuff. Okay, so this is a convex optimization problem. You have to choose a variable x. There's an objective, inequality constraints, equality constraints. The equality constraints are linear, and the objective and inequality constraints are convex, so they curve up, right? So that's a convex optimization problem. What has emerged is sort of the canonical form, or I should say actually the intermediate form, as you would say in like a computer, as a compiler or something like that. The intermediate form, what has emerged is something like this. You minimize a linear function subject to equality constraints and the constraint that the variable x is in a cone. Now, if this is that x is element-wise non-negative, this is a linear program. And by swapping out the cone, you get different other problems. And this is essentially the intermediate form now for convex optimization. And literally I mean that because there are systems that compile something written in a high-level language into this intermediate form. And then there's a whole bunch of people working on actually solvers for this intermediate form. Okay, so why? Well, I mean, this is beautiful mathematics and stuff like that. We can start with that. I think more interesting is that you can actually solve them. I mean, that's actually the interesting part. It unifies a lot of things. So you'd have different problems from very different areas, and it turns out they're very closely related. And this is not obvious. I mean, this would be things like stuff from information theory and circuit design, right? I mean, these are like wildly different fields. In fact, the people in them don't really like each other and are horrified to find out how close some of the mathematics they work on is related, right? So they're very uncomfortable, both ways, by the way. So, and there's just tons of applications. So, and a lot more than previously thought. So I won't say a lot about this, but there's a bunch in machine learning and statistics, finance, supply chain, all sorts of stuff. Control is one. That's one of the things I'll be talking about. Networking, so designing, operating a network, all sorts of other stuff. I think I'll go fast to get to the point. So the state of the art right now is something like this. If you have thousands to 10,000s of variables and constraints, you can solve these by methods that have been around for maybe 20 years now, right? And they're getting better, and there's still places where they're not completely reliable, but it's moving, and it's going to happen. So this is not quite a technology, but it's getting there. One other thing that has emerged in the last 5-10 years is basically high-level language support, domain-specific languages for convex optimization. Okay, I mean optimization in general, but I'm talking about convex here. And the idea is you describe the problem in a high-level language that is automatically compiled into one of these intermediate forms, which is a cone program, and then that cone program is solved by a standard solver, right? So, and I mean, there's a lot more to this, but at the highest level, this is what it is. It's fairly straightforward. Now what this does is it allows you to do rapid prototyping for small and medium problems. And actually it's radically changed teaching, right? Because it means what you can do is instead of it being a pain in the ass to actually solve a convex problem, it's actually writing a 5-line script. And so it means that if you're teaching it, doesn't matter which department the students are from, they're going to do, whether they like it or not, signal processing, vision, networking, circuit design, finance, control, etc. Right? Period. And it's easy. It's like you write a short thing. Okay. One of these, there's several by now. This is the one that's most widely used, I guess. It's in MATLAB, unfortunately. There's ones now in actual languages, in things like Python and Julia. But the idea would be something like this. Here would be your mathematical description of what you want to do. This is a support vector machine classifier. And the idea is to have the source code look as close to the mathematics as possible, right? So that's it. And if you read just a little tiny bit of MATLAB syntax, this will make total sense to you. So this is the idea. So the idea is you'd write this. This thing would be then compiled into a cone program. That cone program would be solved. And then you'd solve this. Now, of course, for a support vector machine, this would be idiotic because there are, in fact, extremely well, because so many people use support vector machines, there would be all sorts of unbelievably optimized codes for doing this, and this would run, you know, at something like 1/100th the speed. Actually, our goal is 1/10. So the goal is to be 1/10 as fast as a custom method, right? So and people sometimes say to me, I'm sorry, didn't you mean you want to be 10x faster? And I'd say, no, we want to be 10x slower. People are like, I don't get it. We say, yeah, because our coding time will be 10 to the 5 times faster, right? So that's the idea. So, oh, I should say the other reason. The other reason is suppose you came along and decided that you wanted the first 10 weights to be positive. And actually, there'd be perfectly good cases where that might be, and you would simply add that as a constraint here, and it would run, right? So, okay. So now we get to what the main point is, which is real-time embedded optimization. So. And what I'll do is sort of just talk about some of the ideas, right? So it turns out that in a lot of cases, these are online applications, you solve the same problem but with different data. So the data changes, right? Obvious ones would be, well, control, right? So in control, you're effectively, or in estimation, you're estimating something or making good actions, but things change, right? Like it's another 1/10 of a second, and you get another, nav update or something like this, and you get, or actually the goals have changed. In finance, it'd be the same thing. You solve a new problem because you have new estimates of returns, risks, all sorts of other stuff, this kind of things. Now, of course, this is actually used now, and it's been used for decades in areas like supply chain, right? So, I mean, this is just completely so people do, and the reason is that the time scales are longer, and so you can solve a big problem, and it's been used in a bunch of areas there. I was going to say what else I was going to say about that. In fact, I'll come back and say something about these two things in a bit. So what's not obvious is this, is it turns out you can actually solve these problems the convex problems in milliseconds or microseconds. These are modest and small size things. And it just turns out you can do this. It's not even that fancy or hard to do. This actually, this is what the talk is about, this changes everything. And I can tell because I was in control, and just to make a caricature of it, the story would go something like this. I would be in control, David would be in OR, let's say, and then someone would come along and say, what do you do? I'm sort of pretending you're in OR if you don't mind. So, and I would say, and you'd say, well, we do supply chain stuff and we estimate how many people are going to order this and the capacity of this and blah, blah, blah. And we have 25,000 variables, and then we solve this big linear program and we decide how much stuff to ship from where to where, right? That's my summary of OR. Right? It's pretty sophisticated, right? And then they turn to me and they say, what do you do in control? And I go, well, it's kind of the same thing. I get updates. Of course, I get them 100 times a second. And then I have to make a decision 100 times a second. And they go, well, what do you do? Do you do all the sophisticated things David does? And I'd say, no, because we have to do it every 10 milliseconds, right? Well, what do you do? And the honest truth is this. We multiply by a matrix. That's true. So you get on an airplane, anything, you start an engine, that's what's happening, not much more. And you have a Kalman filter, maybe you multiply by 2 matrices or something, but basically we're talking like, BLAST level 2, right? Barely, we're talking about 2 matrix vector multiplies, right? That's actually what happens, right? Because, if you have a control system on an airplane, you got 12 measurements come in, and you have to make 8 choices, but you have to do it 10 times or 100 times a second, okay? So then I would say, that explains why I can't solve a giant LP like David. Right, which is the sophisticated thing taking into account warehouse capacity, shipping capacities, all sorts, piecewise linear costs, beautiful, sophisticated stuff, right? And I'd say, well, I can't do that because I have to do this 100 times a second. Oh, and I have to do it without fail. Everybody got this? Right, so, okay. That was the picture I told myself if someone said, well, why don't you in control do these fancy things that these people over here in OR are doing? And I would say, we can't, because it's too hard, right? Anyway, that's all false. It's all wrong. We can solve QPs in milliseconds or microseconds, right? By the way, pretty much no one knows this, or they're ignoring it, or I don't know, or they're whatever, but it's true, right? And actually it's quite interesting because it's not at all clear, people aren't thinking about this. Well, some are, actually more than some. Okay. I'll just give I don't need to give an example, but a quick example would just to show you what an embedded thing might look like is you would need to move. You're going to push something from one place to another by applying a force. You're going to do this. You're going to push on it hard enough. And the limit here is 1. You're going to push on it hard enough that by the time it arrives at its destination, it's going to be shaking if you just push it, because you're going to excite internal vibration modes, right? So it's a convex problem, and you can just solve that, right? And you would get something like that. That's the optimal force you should apply, right? And you can go back and interpret it after the fact, but after a while it's better just to say, screw it, that's just the solution and it came from convex optimization. I mean, that's the right way to think. I mean, you can interpret it. Of course you have to push it to the left if you're going to move it, or push it to the right. Of course you have to push it. And then someone would say, what's that? And you'd say, oh, that's active. I'm actively removing the energy I have inserted into the vibration modes, right? But I mean, it's better off just saying that's the solution, right? So, okay. Okay, so what do you need if you're going to make an embedded solver? Well, you might have hard real-time execution limits, right? So you might say, I need to know it in 1 millisecond, like period. Actually, interesting. Well, okay, I'll skip over that. Actually, what people are actually more concerned about in practice is actually extreme reliability and robustness. So you cannot have a floating point. You can't have a floating point exception, obviously, right? And you have to handle poor quality data. That's not outright fraudulent data, right? If you allege that a parameter is going to be positive, and you pass in the number -10, you have violated. The caller has violated, his contract, and I mean, who knows what comes out? But we're talking about passing in something that's like -1e -5 or something, which seems fair. That's poor. And the other thing is they have to have small footprint, right? This is for real-time applications, right? So you can't be stopping for garbage collection or allocating memory or anything like this. These are obvious things. Okay. So this is what you need for one. Now, if a general solver works, use it. I mean, if you have 5 minutes to make a choice, I mean, not a problem. Just use stuff that works right now. Otherwise, you can develop some custom code by hand. Or you can do it automatically via code generation. And when you do that, you can exploit various things that you would know at solver development time, but not at actual execution, at solve time, right? So you'd separate what you know at compile time from what you know at actual solve time, right? So, for example, the traditional data in a problem, these are the things. This is precisely what you are told when the solver is invoked. Right. The sparsity pattern, however, would be known ahead of time. So, okay. So what happens if you build, actually either way here, is instead of getting, you could easily expect a 10x speed up or 100x. And in fact, what you typically get is things like 1000x. Essentially, almost all of that credit goes to the people who make compilers. Right, so the back end of compilers, because if you give them code that is nearly branch free, they go nuts and they have a lot of fun, and the next thing you know, they reorder all the operations, and the next thing you know, it's fast. So, okay. So the difference would be something like CVX would be a parser solver. So you'd take a problem instance, it would compile it into a cone program, solve the cone program, and that would give you X star. Right. This would be like this. You would describe a problem family. The generator would generate source code, maybe C. No, definitely C. Then you'd compile that with all the flags on, so that all your friends who do the back end of compilers can show off. And you end up somewhat later, with a solver that's now a custom solver that maps problems to solutions. Actually, so that's the idea. And then this would be 1,000 times faster than that. Would be the rough idea. Okay. So this is possible. Actually, we've made like 2 or 3 now. Other people have made a couple. But CVXGen is a very simple one. And this is like out of date, but it's just to show you that it's possible. And the idea is it takes a description of a problem in a high-level language, domain-specific language, and then it emits flat C source, actually library-free source, that is then compiled into a custom solver for that specific problem, right? And the input might look like this. This would be a support vector machine. I mean, it doesn't matter, but so this would be the source input that is compiled then into a flat C source, which you then compile. You turn on all the optimization flags. That's optimization in the compiler. And then you get a solver. And so these are out of date, but it doesn't really matter because the point is that you get things like this. And the main thing actually is just that. These can be much faster now, and it doesn't really matter too much. Yeah?
Do you always, in describing the problem family, have to bound the dimensions by a constant?
No. In this case, for this particular one, you do. Yeah. Although, if you can, that's fantastic, right? Because then we emit basically, it's code that's like extremely explicit. Yeah.
Maybe you're going to cover this, but you also have compilers into silicon instead of just code.
So some people have done. Some people have claimed to do that. I'm a little skeptical. So FPGA stuff works fine now. So that works. So you can compile directly into FPGAs. And people are, at least I know a few instances where people claim to do that.
And how much more speed up do you get?
It's a lot. But actually they're mostly, it turns out it doesn't speed up that much. The power goes way down is what people care about. So yeah. So in fact, for some of those it's slower, but the number of joules is a whole lot less. Yeah. So that's, yeah. Okay, so actually the only thing about the only thing to note about this is to go back. I mean, none of these details matter. These are all off by factors of 5 now. It doesn't matter. The main point, though, is this, which I think, the high-level point is just this. You can solve a quite sophisticated convex optimization problem in things like 50 microseconds. Okay? And the implications of this are not, I don't think, have diffused widely enough, right? So some people in control are aware of this and using it. Others are hoping it'll just go away. It's not going to, right? But you can do this in a lot of other areas as well. So, okay. Okay, so I'm just going to wrap up. So these problems come up in a lot of applications. You can solve them effectively. Medium scale problems, and if you have seconds or more, or whatever it is, to make a decision, you can just do that. That's not a problem. But you can solve small problems at microsecond, millisecond timescales. The other thing is, high-level language support makes a lot of this stuff easy, and you can actually do stuff like the code generation stuff is only going to get a lot better, and there'll be a lot more of it and stuff like that. So, and it's actually going to be interesting because I think, let me just go to what I believe are some of the big picture issues here, right? So it's actually kind of interesting. Things like control. Let's just take one. Signal processing, even like control of networks is another one. A lot of these things were developed when computation was expensive and slow, right? So, even for example, the order of magnitude 10 by 10 by matrix multiplication that you might do in a modern controller now was considered absolutely radical in like 1966 or something like that, right? Because people were using PID control and all that kind of stuff. So, this is the existing situation, right? But now you can solve in the same amount of time, and by the way, with the same reliability, I should add. Right, so that's actually critical, unless that would be the other main, that'd be the other thing people would say. They would say, no, I'll take a matrix multiply because I know it's always going to work or something like that. Then I'm on there. They got a good point there, but you can make these things extremely reliable. So the interesting thing is, you go back and now you rethink a lot of things, and the question is, what could you do? And by the way, the answer in some cases might be you wouldn't do anything different. Right, that's entirely possible, but my suspicion is in a lot of cases you would do things differently. If you knew now that you could you could actually solve a full QP or something like that in the time it takes you to do your matrix operations or something like that. So, okay, so that's actually it. I put us back on time, but maybe we'll have a few questions. Yeah.
One big problem in networking is the time to collect the information and then to send back the control actions. And that does not speed up with the speed of computation.
Yeah, no, that's true in a lot of areas where it turns out, like in things like when you use this in robotics and stuff like that, it turns out what happens is the optimization, when you profile it, goes from 99% down to 2, at which point it's just 0, right? So for example, in robotics, actually just linearizing the dynamics around the current point, you're going to be doing a lot of sines and cosines, and they'll have lookup, but that's going to dominate. So the optimization just goes away. So that's disappointing. In your case, it's disappointing. What can you do, right? So, yeah.
So, my student actually use a lot these libraries in the context of the robotics lab, and in what we'll talk about it tomorrow. That there are two main missing features. It usually works great. Sometimes we need to manually put some things, but in general it works great. So usually in a real-time system, we just get more and more points or variable over time. So we don't want to store everything from scratch just to update another variable line. The second thing is we have now 200 computers on Amazon Cloud that we want to use and distributed. So the streaming and distributed are the two things that we're really missing in one step of the data model. Even in theory, I'm not sure.
Yeah. No, there was a third one. You said you brought up warm starting, right?
Yeah.
Yeah. So warm starting is when if you are doing a real-time thing, typically if you're doing control, you just solve some problem, which is essentially a plan of action over the next 30 steps. Could be 30 milliseconds, right? Then you execute the first one, then you move forward a millisecond, and you do the same thing again, right? So obviously you have a pretty good estimate of what you would be doing because it's your previous plan shifted 1 millisecond. Okay, so for example, these things don't use that. There are other methods that do, but these don't.
Do we have streaming today?
What's that?
Do we have streaming and distributed column explorer?
Oh no, so streaming is handled in control and in a lot of signal processing is handled in a very ad hoc way that works just perfectly. And you just take a horizon, and that's the end of that, right? So, for example, for streaming, I'm estimating a parameter in streaming, I simply look at the last 100 is a parameter, I look at the last 100 samples, that's where I'm allowed to revise my history, I solve a convex problem to estimate what happened over the last 100 samples, but outside that 100 long memory window, the decisions made past there are locked down, so they're just fixed. That streaming, it works just fine. It works fine. I mean, depending on.
No, it doesn't work for us. That's why we're looking for more theoretical.
Oh, okay. Well, maybe you didn't do it right.
Open, you say,
What?
As far as you know, it's still open?
Is what?
It's still open. I mean, to have theoretical guarantees for this kind of problem.
There. I mean, there are. I know specific instances where there are guarantees that this will work. But, yeah.
Are there any implications for non-convex optimization?
There are, because a lot of, some non-convex optimization is based, specifically things like global optimization are based on solving a sequence of convex optimization problems. And so if you have real-time stuff that speeds things up 1000x, you can actually do like small integer programs and things like that. So there are some implications for that. Actually, I'm glad you asked that question because I should tell you that I actually was someone who did like hardcore circuit design who kind of set me straight on a lot of these things, right? So I showed some optimization problems. I said that's the global solution. That's the whole point. And the guy looked at me and said, no, you have no idea what you're talking about. That's not the global solution. I said, well, actually it is, as it happens. He said, well, how could you know? And I said, well, it has to do with the mathematical properties of the functions and blah, blah, blah. I said, I know it sounds like a ridiculous assertion, but it's actually the global. And he said, no, you could use a different circuit topology. And I was like, you're right. It's the solution for the circuit topology. And then he said, now I'll tell you why this is good. He said, forget all your global stuff. Just go take that back to your university or whatever. He said, I'll tell you why. He said, this is good because it's reliable, and it starts from nothing. He said, you don't have to start from a good guess, and then we give you a refined thing. It starts from 0, and it always works. And I thought about it for a while, and I realized, of course, he was right. So anyway. Which actually fits in well with real-time decision making, because here's what you really want in real-time decision making is you want something that is unbelievably reliable, and we'll just leave it that way. That's what you need. So yeah.
So what is the bottleneck for large problems? Is it the computation time, is it the memory, is it numerical instability, or?
What do you mean by a large problem?
Say 10,000 or 100,000 variables.
Those are not large. That's small. That's anything you can that you can do on a single thread on a single. That's small. So the limits here would be the limits. One is how much can you stick on a GPU? That's one limit, and that is just data size. So GPU is one chunk. Another is how much can you fit on common memory. So if I can get things to 100 gigabytes of data and I can have 64 cores or something, that's another threshold. And then beyond that, you would get to much bigger things. And then I think beyond that, I would call it large scale. So, and there's different methods for all these things.
That's great news, but I guess it also depends on say for some power system problems, I guess the problem typically are real condition. So there seems to be numerical issues, perhaps in MATLAB, even at say 50,000 variables.
Yeah, you know, less and less. I mean, for first order methods, yes, the answer, of course there is, right? Then you have preconditioning to improve that or something. But actually, for the things I was talking about here, I mean, this is just for small and medium-sized things. You could use interior point stuff, and then it's like 2 orders of magnitude less of an issue.
Okay, so we'll move to the next thing for the GAN.
Thanks.